Hello friends, this is Isro question paper, heat transfer part 6. An adiabatic heat exchanger is used to heat cold water at 15 degrees Celsius entering at a rate of 5 kg per second by hot air at 90 degrees Celsius entering also at rate of 5 kg per second. If the exit temperature of hot air is 20 degrees Celsius, the exit temperature of cold water is how much? It's a adiabatic heat exchanger. Adiabatic heat exchanger. Data given for cold inlet cold fluid inlet temperature is 15 degrees Celsius. For cold fluid mass flow rate is 5 kg per second. For air is hot. Inlet temperature of hot fluid 90 degrees Celsius. Mass flow rate of hot fluid is also 5 kg per second. THE given. For air, exit temperature of hot fluid given 20 degrees Celsius. We asked TC exit temperature of cold fluid. We have to calculate. We know heat gain by cold water is heat loss by hot air. So m dot c cold delta c cold m dot c hot into delta t hot. We'll put the values for water. Cp of cold fluid is 4.2. You take Cp of hot is 1.005. So here 5 into 4, so delta C is Tc minus 15. Here 5 into hot water, Cp is hot air, Cp is 1.005, take 1. Here 90 minus 20. 5 cancel. 4 into exit temperature of cold fluid. So 4 Tc is 130. Tc exit temperature of cold water. It will come 130 by 4. It will come nearly 32 degrees Celsius. From option B is the answer. Log mean area A can be given as, for example, if we take a parallel flow heat exchanger, it will come inlet hot fluid inlet temperature, here hot fluid exit temperature, here cold fluid inlet cold fluid exit temperature, here delta T I or delta T1 you can take, THI minus TCI, difference of this temperature and this temperature. Delta T2 at exit is difference of THE minus TCE. So delta Tm is delta T2 minus delta T1 divided by log delta T2 by delta T1. Similarly, mean area is A2 minus A1 by log A2 by A1. Both are important. In this question, this one asked. A2 minus A1 by log A2 by A1. C is the answer. Nusselt number is the ratio of Nusselt number. It's Hd by K. D is the characteristics dimension. V by A. Here Nusselt number is conductive and convective resistance ratio. B is the answer. Also Nusselt number is heat convection by heat conduction. Both B and this one both are important. Heat convection by heat conduction. This is same as RTH conduction by RTH convection. So in this question, B is the answer. Conductive resistance, this one by convective resistance. An adiabatic heat exchanger is used to heat cold water at 15 degrees Celsius entering at a rate of 5 kg per second, hot air at 90 degrees Celsius entering also at a rate of 5 kg per second. If the exit temperature of hot air is 20 degrees Celsius, exit temperature of cold water is how much? This one already asked in 2012 question. Same question repeated in 2013. In 2013, around 8 questions they asked from heat transfer. So if you already discussed in my previous video, what are the data I am writing? Hot fluid inlet temperature and mass flow rate 5 kg per second. Hot fluid exit temperature also given as exit temperature of cold water TCE. So heat capacity TCE. Heat gain by cold water is heat loss by hot water. Heat loss by hot air. Putting the data for cold water it's 4.2. You take 4 TCE we have to find. This is 15. 5 into for air Cp is 1.005. You take 1 T minus 20. So if you calculate this one, we will get 32 degrees Celsius. Exit temperature of cold fluid or water. It's B is the answer. For a given combined radiative and convective heat transfer coefficient H and given thermal conductivity K, critical thickness of insulation for cylinder and sphere is given as. This is very important for all exams. For cylinder it's K by Ht and for sphere it's multiplied to 2K by Ht. B is the answer. here this is Ri, R suffix I, this is R, outside convective heat transfer coefficient, and K, this is insulation. We have to find the, here I will draw two graphs, both are important. Here this graph is versus Q versus R. So if you start from here without any insulation, and this is your critical RC, and this is RI, Q without insulation, this is Q maximum. This is for maximum case. And for cylinder and sphere. For cylinder, RC is K by HO, and for sphere, RC is 2K by H. Both are important. HO is outside heat transfer, convective heat transfer coefficient. K is insulation thermal conductivity. Another graph also important. This is for RTH versus R. So this is R total, and this is R for conduction, resistance for conduction, this is thermal resistance for convection, this is critical resistance. Up to critically RTH thermal resistance in convection is greater than convection thermal resistance, and beyond critical conduction resistance is greater than convection resistance. And here up to critical total resistance decreases, and beyond critical it will increase. So same I am doing again, Q by R, this is RC, RI, Q maximum. Both graphs are important. Match the following: P compressible flow, Q free surface flow, R boundary layer flow, S pipe flow, T heat convection, U Reynolds number, V Nusselt number, W Weber number, X Froude number, Y Mach number, Z skin friction coefficient. Compressible flow for Mach number, free surface flow it's for Weber number is W, Then boundary layer flow, its skin friction coefficient Z. Pipe flow, Reynolds number U. Heat convection already discussed, Nusselt number V. So YW ZUV, it's D the answer. A spherical thermocouple junction of diameter 0.706 mm is to be used for the measurement of temperature of a gas stream. The convective heat transfer coefficient on the bead surface is 400 watt per meter square Kelvin. Thermophysical properties of thermocouple material are K equal to 20 watt per meter Kelvin, C equal to 400 joule per kg Kelvin, and R we can write rho. Density 8500 kg per meter cube. If the thermocouple initially at 30 degrees Celsius is placed in a hot stream of 300 degrees Celsius, the time taken by the bead to reach 298 degrees Celsius is how much? Without calculator, it is very difficult. So its formula is theta by theta I e to the power minus Biot number into Fourier number, or theta by theta I equal to e to the power minus HAT by rho VC. Rho here we take density instead of R. Put the data. Theta is final temperature difference and theta I is initial temperature difference. Here Biot number is HLC is characteristic length HLC by K. Fourier number is alpha T by characteristic length square. Put the data. Here LC for sphere, characteristic length is R by 3 or D by 6. V by A, volume by surface area. If we will do this one, it's R by 3. It's volume by surface area. V by A, volume is 4 by 3 pi r cube divided by 4 pi r square. So it will come R by 3. If you take in D term, it's D by 6. In this question, data are L by LC we got 0.706, it's in mm, so divide LC D by 6, so by 6 into 1000, it's in meter. All are in meter, so convert it into meter. Then convective heat transfer coefficient H is 400 watt per meter square Kelvin. Unit also important. Thermophysical properties K equal to 20 watt per meter Kelvin. C specific heat is 400 joule per kg Kelvin. Then R or rho is 8500 kg per meter cube. And theta I and theta is final temperature difference, 298 minus 300, it will come minus 2 degrees Celsius. Theta is initial difference, 30 minus 300, it will come minus 270 degrees Celsius. So we'll do part. H A T by rho V C. It's H G by B by A is characteristic length, LC into C. So put the values. H is 400, T we have to calculate time, density how much, 8500 into LC we got 0.706 divided by 6 into 1000. Then C specific heat, C is 400 joule per kg Kelvin. So 400 cancel. By using calculator, if you will do 0.9998 T. So theta I already we got 298 minus only theta minus 2 degrees Celsius, and theta I initial difference is 30 degree minus 300, so it's 270 degree Celsius. If we put all in our formula, theta by theta I e to power minus HAT by rho V C will get minus 2 by minus 270 e to power minus 0.9998 T. Take logarithm 2 by 270 equal to minus 0.9998 T. So we'll get minus 4.905 equal to 0.9998 T. Finally, T will get 4.906 seconds. From option 4.9 B is the answer. Two insulating materials of thermal conductivity K and 2K are available for lagging a pipe carrying a hot fluid if the radial thickness of each material is the same. This is also important. Which one you have to put in inner side and which one in outer side. So better you put inside that less conductive material having lower conductivity, and outside you put that material having higher conductivity, K and 2K. This is better. So from option, material with higher thermal conductivity should use for inner layer. No. Material with lower thermal conductivity should be used for inner layer, and one with higher thermal conductivity for the outer. This is correct. B is our answer. For a given heat flow and for the same thickness, the temperature drop across the material will be maximum. So for a given heat flow, same thickness, temperature drop across the material, Q equal to Ka Q by del L. So Q is proportional to K, thermal conductivity. In this case, temperature drop, K is inversely proportional to temperature drop. So temperature drop will be maximum, delta 2 will be maximum when K will minimum. So from option copper, steel, glass wool and refractory bricks. Glass wool is having lowest thermal conductivity, so it will give maximum temperature drop. So C is the answer. List 1 and list 2 matching. A Fourier number, B Weber number, C Grashof number, D Schmidt number. All numbers already discussed in my separate video. You can check it in my playlist. All important number, for all important number I make one separate video. So you check that one also. It will helpful. Fourier number and Biot number, these two are important for transient heat conduction. So 5. Then Grashof number, it is for natural convection. Schmidt number for mass diffusion. Weber number for surface tension. 5136. 5136. B is our answer. In radiative heat transfer, a gray surface is one, A which appears gray to Y, no, whose emissivity is independent of wavelength. Yeah, this is correct. Gray surface. And 3 other body are important. Black body, white body and opaque body. In black body, absorptivity is 1, reflectivity is 0 and transmittivity is 0. And in case of white body, its reflectivity is 1, absorptivity is 0 and transmittivity is 0. For opaque body, transmittivity is 0, absorptivity and reflectivity, if you add absorptivity and reflectivity, it will 1. All 3 are important. For the same inlet and outlet temperature of hot and cold fluids, the log mean temperature difference LMTD is how much? It is already discussed in my previous video. How to calculate that LMTD. Delta T1, delta T2. For example, I am taking parallel flow heat exchanger. Delta T1 is difference of THI inlet fluid, inlet hot fluid inlet temperature minus cold fluid inlet temperature. Delta T1 and delta T is hot fluid exit temperature minus cold fluid exit temperature for this case, for parallel flows. And delta Tm, this is d delta T2 minus delta T1 divided by log and delta T1. So it's greater for counter flow heat exchanger. For counter flow heat exchanger, come like this. Hot fluid inlet temperature, hot fluid exit temperature. This is cold fluid inlet temperature. This is cold fluid exit temperature. Delta T1, T2. Same delta Tm I have to calculate. So it's greater for counter flow heat exchanger for parallel flow heat exchanger. B is the answer. Thank you friends. Thank you for watching my video. This is end of 2013 Isro question paper heat transfer, and in that year around 8 questions they asked from heat transfer. Out of them, one is very difficult. It means it's calculative. It took around 4 to 5 minutes. Others are you can solve within 1 minute. Thank you friends.